Hey everybody, sorry I couldn't be there today. I am at the ADL assembly for the freshmen and um, sophomores. So I don't want to waste a day, so I wrote two screencasts that will cover these two questions. So the first question, you should try to get as far as possible as you can. All the things work the same, except now we're adding that little extra piece of friction. So um, we have to determine a couple things and use that information to ultimately solve this whole problem. First, we have to look at just what we have. We have a 500 Newton block that is resting on a 20-degree ramp. So we draw that. Force of gravity is always straight down. That's 500 newtons. And our normal force goes up kind of like that, which means we got the FGY and FGX that we have to figure out. So my FGX is the thing that's pulling me down the ramp, my FGY, the thing that's counteracting my normal force. Remember that friction, just write it over here, friction is found by the coefficient of friction multiplied by the normal force, but it also can be figured out just from what we've done in the past. We know that on a free body diagram, I know a lot of you are rotating it, so I will rotate this back where our normal force is up. We have to calculate all of these, which means not our FG, this was a common thing on the quiz, not our FG goes down, but our FGY is the piece that gets rotated purely vertical. The friction force, the problem says, is the only thing that is stopping it from sliding down the ramp. Down the ramp will be to the left, and that's being pulled due to the FGX. So we have to find all these things, and we know that FGX and FGY are found by FG cosine theta, and FGX is FG sine theta, where theta is the angle of the ramp, 20 degrees. So our FG is just the 500 newtons. 500 times the cosine of 20 degrees, and while I'm setting that up, 500 times the sine of 20 degrees. Get those numbers, and I get 500 cosine 20, 500 sine 20, 469 for 500 cosine 20, 469.84 newtons, and 171.01 newtons for my FGX. So on my free body diagram, my FGX 171.01 newtons. My normal force, I don't know yet, but I know my FGY is 469.84 newtons. It says this thing is stationary, resting on a ramp, so that tells us that obviously the normal force has to cancel with FGY, so the normal force is also 469.84, because these two have to equal and opposite each other. And since this is totally at rest, the force of friction has to cancel with the leftward force, which is FGX. Force of friction is up the ramp, going that way. FGX going parallel down the ramp. They have to equal each other because there can't be any net force if it's stationary. So that means that our force of friction, which in this case is a static friction force, is 171.01 newtons. So that is part A. The value of our static friction force is 171.01 newtons. But now the question moves on and says we are pushing the block, which means we're breaking that static friction bond. We don't know exactly what the maximum is, but it has to be more than 171 because we're still static. So the ramp can push back upwards a little bit more. But again, we don't know exactly what it is. But we know now, if we give it that push and break the static friction, we move into kinetic friction. And we have to figure out what our kinetic friction force is. Well, really, ultimately, we have to figure out what our net force is. And to do that, we have to first figure out the kinetic friction force. So what happens is our free body diagram changes just slightly. It changes because our FGY is still 469.84. Our our F normal also 469.84. But our force of friction is no longer the static friction force. It is the kinetic friction force. But gravity's still pulling just as hard, so this is still 171.01. So to figure out what the difference is between left and right forces, we've got to figure out what FFK is. And FFK can be found using this equation. Force of kinetic friction equals the coefficient of kinetic friction times the normal force. And that gives us, we know our kinetic friction coefficient is 0.1. So that's 0.1, which is our mu, times our normal force, which is 469.84, which gives us, I don't need a calculator for that, we can just say 46.98 newtons. So our kinetic friction force is much lower, as it always is, and it's 46.98. Sorry, that trailed off a little bit. 46.98 newtons is our kinetic friction force. So now we have the two forces left and right, and those are the only two forces because that's what it says. So to figure out what the acceleration is, our acceleration is our net force. And our net force, that cancels with that. The FGY and the normal force cancel. So there's no vertical motion. And we do right, which is 46.98, our kinetic friction force, minus left force, 171.01, which gives us 124.03, really negative 124.03 newtons. Sorry, that's not A, that's our F net. Negative 124.03 newtons. To find our A, it's F net over M. We don't quite know what our M is. Well, we kind of do. It's 500, which is our weight, over 9.8. So our M equals 500 over 9.8, 51.02 kilograms. So we can use that piece of information and divide our net force by our mass, 51.02 kilograms, to get an acceleration of negative, the reason it's negative is because negative means down the ramp, 2.43 meters per second squared. So we have solved the problem. DTR stands for down the ramp. We found the acceleration. We used our kinetic friction force coefficient to determine what the kinetic friction force is once it's moving, because it's going to be less than the static friction. And we use that to find the acceleration. So hopefully this helped. The worksheet you have obviously has different numbers. You should have seen that by now. But you should be able to apply this in the same manner to that same exact type of question. So, good job, and I will check on this tomorrow.